Let's see. Is it working? Is there audio? Yes, there is. All right. Okay, so day 2 of making a small VM in Rust. Since the last time, I just quickly cleaned up the code so that I can actually access the registers with an index. So now the struct that holds all the registers has like indexed implemented for it, so that I can just do register like with an index like so. It's quite ugly, but yeah, whatever. I just want to focus on actually implementing the operands and the operators, and not actually spending all my time fiddling with like having less lines of code. So yeah, but besides that, I also now read binary data from memory, from std_in, and put it in the programs, in the VM's memory. So yeah, copy from slice, and I read a stream of bytes, and then I convert those bytes into U16, and then put all of that in memory. And then yeah, the rest hasn't changed much. I just now have an add instruction. So yeah, that's pretty much it. Maybe I could actually here I could stop the PC max is equal to PC equals bin. It's more like to avoid it looping to infinity for now. Registers PC. So can I do that? Yeah, I can. So now if I run the thing, with my little compiled thing, we can see that we actually can parse the operands, and so here we have an add, but of course our add is only has zeros, so yeah, that's it adds 0 to 0, you know. I assume, if it works. But anyway, we can actually recognize which instruction it is, so that's cool. Maybe I should clean this up as well. Find a way to display this slightly better. But oh well, we'll see. So yeah, that was the add instruction that we did yesterday. And now we were at the LDI instruction. LDI stands for load indirect. This instruction is used to load a value from a location in memory into register. Yeah, that makes sense. It's like the regular load instruction. The specification can be found on page 532. Here is what the binary layout looks like. So we have an opcode, we have a destination register, and we have a PC offset. Oh, so it's an offset compared to the program counter, not a direct address in memory, which is quite strange, I think. Yeah, okay, sure. In contrast to add, there are no modes and fewer parameters. This time the opcode is 1010, which corresponds to the op_LDI enum value. Just like add, it contains a 3-bit DR, destination register, for storing the loaded value. The remaining bits are labeled PC offset 9. So there is 9 bits of offset. This is an immediate value embedded in the instruction, similar to IM5 for the add. Since this, okay, and the number at the end, so imp5 was just like, it's 5 bits, and here PC offset 9 just means it's 9 bits. Okay, sure. Since these instruction loads from memory, we can guess that this number is some kind of address which tells us where to load from. The specification provides more detail. An address is computed by sign extending bits. 80. Oh, right. We have to, like, this is an integer, not an unsigned integer, so we have to adjust it to 16 bits with the function that he gave above, this one, sign extend, so just pushing like the sign bit to the beginning of the number. Yeah, that sounds fine. 16-bit. Wait, an address is computing by sign extending bits, yes, and adding this value to the incremented PC program counter. What is stored in memory at this address is the address of the data to be loaded into DR. Oh, okay. I still wonder why it's an offset and not a direct address. Maybe a direct address is just too large to be stored there. Just like before, we need to sign extend this 9-bit value, but this time add it to the current PC. If you look back at the execution loop, the PC was incremented after this instruction was loaded. If you look back at the instruction loop, the PC was incremented. Okay. Is it before or after we incremented? That's a bit confusing. The resulting sum is an address to a location in memory, and that address contains yet another value, which is the address of the value to load. This may seem like a roundabout way to read from memory, but it is indispensable. The LD instruction is limited to address offset that are 9 bits, whereas the memory requires 16 bits to address. LDI is useful for loading values that are stored in locations far away from the current PC, but to use it, the address of the final location needs to be stored in a neighborhood nearby. You can think of it like having a local variable in C, which is a pointer to some data. Okay. I still don't see why it needs to be an offset, but anyway. So LDA sample. The value of far data is an address, yeah, of course. Far data itself, the location in memory containing the address, has an address. Yeah, okay, so the pointer has an address itself, sure. In memory, it may be laid out like so. So this far data, this is a string. If PC was at 100, LDI R0, so we would do plus, so this would be 1, 2, 3, which would give us that. Okay, it's not directly the location of the memory, it's the location of a pointer to the actual memory. Okay, sure. Why not? I guess that's more efficient. Okay, it's to indicate like a local variable that actually has the address inside of it. Okay, yeah, that makes more sense. Same as before, the flags need to be updated after putting the value into DR. The condition codes are set based on whether the value loaded is -0 or positive. Here is the code for, in this case, memory will be discussed in a later section. So destination register is the same as before. PC offset is, oh, we need to sign extended, but okay, that makes sense. Register R0 memread. So we first read the memory of the pointers that stores the address, and then we memread the address that is pointed. Okay, there is 2 levels of indirection already. Okay, sure. Okay, that makes sense. Okay, sure. Let's quickly implement that. FNLDI takes again registers, mute register, and an instruction. Sure, it returns nothing. Then we get this, we get dr the same way as before. Yeah. Then we get the PC offset, which is equal to sign extend, and we sign extend instruction, which will be 0b. Well, actually, in hexadecimal this time it makes sense, so it's 1 and then 8 ones as well. So 9 bits of ones. Then bit counts is 9. Okay, sure. Then we do registers. dr is equal to do for now. So it's the mem read stuff. Mem read registers. Oh, well, I can actually do just PC in my case plus PC offset. Okay, and finally, again, we update flags. Yeah, flags. Don't I have this? No, I do. Oh, it's a method. Registers update flags. Of again dr. Unexpected token is up. This still compiles. Okay. Okay. As I said, this instruction shared a lot of code and knowledge learned from add. You will find this is the case with the remaining instructions. You now need to go back and implement the rest of the switch case for the instructions, follow the specification, and use the code listed here to complete the others. The code for all instructions is listed at the end of this tutorial. 2 of the opcodes specified before will not be used. They are RTI and res. You can ignore these case or throw an error if they are executed. After you are done, the bulk of your VM will be completed. Really? Okay, nice. Okay, let's try to read the specification. The specification, how long is it? It's very small. Why did he say like page 500 something? It's crazy. So here are all the instructions detailed. Should probably download this. Yes. Okay. Should probably download this. Yeah, I don't know if it's really readable from here. DL and it's LC3 something this LC3 to specification LC3 specification.pdf. Oops. Sure, LC3 specification PDF. Okay. And this can go there. Okay. Now let's see if Wait, what? Ah, okay, so it's like a part of the specification, maybe, because this is 522. Okay. Damn, I look extremely white now. Is that better? Yeah, probably. Where were the specification of the instructions? Here we are, okay. Oh, there is other modes. Oh no, never mind, it's AND. So for example, AND is the same as add, but with a different opcode. There is not, again. Oh, is it the same? Not is different. Oh, there is no sub or multiply thing. Okay. So there is not, there is no or is it? Wait. And BR. Jumbret. Okay, so there is a jump, JSTR, JSRR, load indirect, load direct? Not sure. So the not would be, yes, okay. So the not would have like the destination register, an operand register, and then a bunch of ones. So this is just like padding, basically, right? Description of the bitwise or complement of the content of SR is stored in DR. The condition codes are set based on whether the binary value produced taken as 2's complement is negative, 0, or positive. The condition code is like the condition register. Okay. Okay. What else is there? What is layer? Load effective address. An address is computed by sign extending bits to 16 bits and adding this value to the incremented PC. This address is loaded into DR, the condition codes. Okay, so this is like one pointer dereference and the LDI is 2 pointer dereference. An address is computed by sun extending this and adding this value. Okay, that's the same. What is stored in memory at this address is the address of the data to be loaded into DR. The condition codes are set based on whether the value loaded is negative, 0, or positive. And finally, LDR is load base plus offset. Okay. So it's mem plus base R plus... What the fuck is sext? Come on, I'm trying to not be childish, but... Oh, sext. Oh, sext is sign extend. Okay. Okay. That makes sense. Okay. Let's go back to just the table. The table. So we are sure that add and end are exactly the same, so I can implement end quite easily, I think. I can do binary up this, and then we have previous arguments. So, like so, and then we just do fn add is registers, instruction, and it's just basically binary up, yeah, this, and then this is, I don't know, is there ops add? Hmm. Oh, never mind. That's my own function. Well, whatever. Can we do x, y, x plus y, like so? Then we can write AND very easily. This is just binary AND. Okay, and so we have add. Oh, where's my... Oh, AND is later, okay. Okay, that's AND. And LDI is LDI. Max, oops. Yeah, sure, that's good. Mute registers. Okay. Okay. There's a trap thing which I do not understand whatsoever. Let's see. What is BR? So we have add, we have AND. And let's just quickly check that this is the same. Yeah, this is the same. They just replace the plus by an AND. Yep, that's fine. Okay. BR, conditional branch. Maybe I should name the thing before I forget. Where is my... Oh, BR, okay. Conditional branch. Because I think jump is just branch, you know? So assembler format label this. So it has an opcode of 0, then NZP, then a PC offset. So operation if n, what is n? The condition code specified by the state of bits. Okay, those 3 bits. Those are compared against the condition, and if they match. Okay, I see. If those 3 bits are the same as the condition flags, then it's good. Then it does PC is equal to... it changes the program counter to the PC offset. Okay. The condition code specified by... maybe I should unzoom a little. The condition code specified by the state of bits are tested if bits 11 is set and is tested if it's not tested. If any of the condition codes tested is set, the program branches. Hi, hey, what's up? The program branches to the location specified by adding the sign extended PC offset to the incremented PC. Sure, okay. And they have like branch if negative, branch if 0, branch if positive. That I don't know what the fuck that is. Branch if 0 and positive. Okay, let's try this. Let's try to implement this. Where's my... Okay, let's just add fnbr, which is also going to take just the registers, instruction, like so. Actually, maybe all of these take a mutable reference to register, so those should all be into the register struct. But yeah, whatever. Let's just implement them all and then see. So we let check bits MCPN, and I couldn't chat with my original account. Oh, okay. I understand. YouTube is trying to censor. What did you post on your previous channel? And so we need those things. So this would be kind of like this, but I think it's the same actually. Since it's only 3 bits, and then if you go back to like an AND, it's only 3 bits after the thing as well, so yeah, it's the same. Okay. Nothing bad, I'm innocent. Oh. Yeah, I don't know. You can send a mail to customer support then. Should be good enough. Condition bits like so. And so we could just do let n is equal to condition bits. This. Then z is condition bits 1 ended with this. Okay, okay, I think it's... Wait, no. I first need to end them, like so. And this gets shifted by 0, this gets shifted by 1, and positive gets this, and gets shifted by 2. Then and we can all think those were condition. So I need to check the condition register. Can do... What do you mean by VM exactly? It's like the... Well, it's a virtual machine. It's from this. It's like a toy VM, kind of like a educational thing where you just parse machine code and yeah, just execute it, I guess. And you can probably, there is some compiler out there that compiles something like probably assembly from this into machine code, and then I will hopefully be able to put that in my VM. Boom, 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 boom. So we have the thing, and if we do like match registers cond like so, and we do cond pause like so, blah. 0 neg and if n is equal to 1. So this is like we can reverse those, I guess. If this is n and this is z, this is p. Well, actually, I didn't need to do that. Whatever. That's a bit of a weird way of doing things, but in any other case, I can return false. Looks fun, I'll try it too. Yeah, you should. It's nice. It's quite fun. And we do let matches. Well, maybe just condition past. Yeah. And we do if condition. I should rewrite this. This is horrible. This is horrible. Yeah, whatever. Whatever. If condition passed, then we do registers PC plus equal to we need to let PC offset is equal to instruction left shifted by nothing. Actually, we just need to do instruction ended with 0x1ff. I think it's 9 bits, right? Yeah, it's 9 bits. So we just get the PC offset, and then we add the PC offset to this, but we need also to sign extend this, and it is 9 bits. And yeah, I think that's my BR implementation, so branch. So we can add BR now, registers, instruction. This is a mutable reference. Up. Does it still compile? FN once. Argument 2 of type is missing. Oh, my bad. I forgot in the this to replace this by a comma. Okay, still a lot of warnings, but oh well. I need to do this. Oh well. What's the next one? Jump ret. Returned from subroutine. Boom. So there is jump SR, so maybe jump SR is jump subroutine. There is not as well, that seems easy enough. There is ret, RTI, ST. Let's try to do not. What does the plus mean? No, the plus indicates instruction that modify condition codes. Oh, okay, I see. Okay. Okay. Can I do quickly not instruction. And so the not instruction is let's see where it is. Bitwise complement. Okay, so you just do dr sr and you not it, and this is just a bunch of ones. Okay, sure, that's fine enough. Let's can I just stop it? I would like to stop my LSP, please. Whatever. I'll keep the ugly things there for now. So let's just get destination. Well, we already have the code for this. I think this is the same. Yep. Yeah, that's it. And then we just do registers. dr is equal to not registers sr1. Well, it's just SR in this case, since there is only one operand, and this. Wait. Huh. Like the exclamation mark is actually used in Rust to do bitwise not. Okay, sure. I mean, that actually makes a bit of sense. The bitwise complement of the content of SR is stored in DR. The condition codes are set based on whether the binary value produced taken as 2's complement integer is negative, positive. Ah, okay. So set cc. We can do an update flags after, I guess. I guess. Yeah, let's see what else is there in this tutorial. Okay, he asked me to complete some of this. There is some instructions that are completely useless, so I think we can panic if we encounter them. Res and RTI instruction are valid. Yes. Okay. Okay. Instruction cheat sheet. This section contains a full implementation of the remaining instruction if you get stuck. These are news, okay. Bitwise and is the same. Bitwise not, I just did. Branch, I just did. Oh, I can just simplify by doing this. Well, he can. I don't know if I can. But anyway. Yeah. Well, anyway, it doesn't matter too much. I can do it later. Oh yeah, I actually have this already. Wait, maybe I can do this. Just bitwise AND instead of doing my ugly match. Where's my ugly match? Yeah, that's it. If condition bits and registers count is different than 0, like so. We can do something like this. I can. Finally. Oh, wait, never mind. Maybe I cannot. Oh yeah, it's just... all of this can be removed. Okay, that makes... oh, fuck. Maybe I cannot. Move occur because type count which does not implement the copy trait. Well, it can implement the copy traits. It's fine. It's 3 bits. Okay, finally. Okay, that's nice. You can convert enums to integers very easily, but converting integers to enum is kind of tricky. Okay, which makes sense because when it's an enum, you already know that it's limited to some integers, but if it's an integer, it can be anything. So unless your enum is like the same size as the integer, it doesn't quite work. Okay. So there is so this is the branch, this is the jump. Ret is listed as a separate instruction in the specification since it's a different keyword in assembly. However, it is actually a special case of jump. Ret happens whenever R1 is 7. Okay. So we get R1 and we just set it. Oh, okay. That I can probably... okay, but there is a bunch of stuff. But yeah, it's okay. I can do them in my own time. Trap routine, yes. That sounds a bit better. I'm gonna take a small break. And then after it, I think I will just try to do this, because it seems like with this kind of thing, I will finally be able to output something on the screen, which would be nice. So yeah. Alright. It's better when I have coffee. So trap routines. LC3 provides a few predefined routines for performing command tasks and interacting with I/O devices. For example, there are routines for getting input from the keyboard and for displaying strings to the consoles. These are called trap routines, which you can think of as the operating system or API for the LC3. Each trap routine is assigned a trap code which identifies it, similar to an opcode. Okay, so it's like, yeah, an interrupt. Kinda? It's like a syscall, is what I mean. To execute one, the trap instruction is called with the trap code of the desired routine. Okay, so it's just a bunch of ones, a bunch of zeros, and then a trap vect. And so there is a trap code. So trap get C, get a character from keyboard, not a code onto the terminal, output a character, output a word string. A word string? Oh, a word as in like a U16. Okay. Get character from keyboards, echo to the terminal, output a byte, string, halt the program. You may be wondering why the trap codes are not included in the instructions. This is because they do not actually introduce any new functionality to the LC3. They just provide a convenient way to perform a task similar to OS system calls. In the official LC3 simulator, trap routines are written in assembly. When a trap code is called, the PC is moved to that code address. The CPU executes the procedure instructions, and when it completes, the PC is reset to the location following the initial call. Okay. Note, this is why programs start at address 300 instead of just 0. The lower addresses are left empty to leave space for the trap routine code. Oh, I'm gonna have a fun time putting that in Rust inside the memory itself. There are no specifications for how trap routines must be implemented, only that they are supposed to do only what they are supposed to do. In our VM, we are going to do things slightly differently by writing them in C. When a trap code is invoked, a C function will be called. This is completed instruction. When it's completed in instruction. Okay, I can just have like a bunch of functions that output a character or anything and just call those directly in Rust. Like, don't really care about putting those directly in the program's memory, I think. That's kind of overkill for now. If you're curious about trap codes in assembly, see Ryan's implementation. So here's a VM. Load file, load OS, VM sign flag. Seems cool. Even though the trap routines can be written in assembly, and this is what a physical LC3 computer would do, it isn't the best fit for a VM. Instead of writing our own primitive IO routines, we can take advantage of the one available on our OS. This will make the VM run better on computer, simplify the code, and provide a higher level of abstraction for portability. Note, getting input from the keyboard is one specific example of this. The assembly instruction uses a loop to do continuously to continuously check the keyboard for input. This consumes a lot of CPU time for nothing. Using a proper OS input function allows the program to sleep until input is received. Okay. Okay. Let me quickly copy paste this. So the trap will be right after the up thing. Trap like so. Like so. That. And you can put all that in lowercase. It's fine. So after all this, we can have fn trap. I don't know what it does yet. Well, I still think it probably needs the register and the instruction. And so it's just a switch on the instruction. And we get the last 8 bits to get the trap code. Okay. So let's trap code equal to instruction like so, and then we just do this match on trap. Let's maybe yeah, sure, trap code maybe, and then we do trap. Just have a switch like so. Panic, invalid, trap code, this, trap code. Up, that should be okay. This, can I do this as U16? I cannot do that. That sucks. That sucks. Can I just imp from U16 for trap, like so. Fn, yes, this, and then I just match value. Ah, that's kind of cringe though. That's kind of cringe. That is quite cringe. I don't want to do that. Why Rust? Why? That kind of sucks. Oh well. Once again, I don't want to worry too much for now. I can do the cleaning later. I'll do whatever is necessary to advance for now. Oops. Like so. Like so. Oops. And this will be just the values above as well. Up, like so. This will be this. And this is trap. This is just a comma. Commas everywhere. Up. So. Okay, and this can go here. Value like so. Yes. And now I can just do let's yeah, just that trap. So I need to call into. Yes, finally. Okay. With the instruction, it will show you how to implement a single trap routine and then leave the rest to you. Okay. The put s trap code is used to output a null terminated string, similar to printf in C. The specification is found on page 543. To display a string, we must give the trap routine a string to display. This is done by storing the address of the first character in R0 before beginning the trap. Okay. So before the traps, like the arguments are passed via registers and stuff, which makes sense. It's basically how you call just functions in C in assembly as well. So match trap code, and for now we'll say do like so, and we will do put s first. Okay, and so we get the string, and then we just put char. Okay, seems easy enough. Seems easy enough. Let's I don't know, string as u16 is equal to. Oh, I need the memory here as well, I guess. Memory, which is gonna be a mutable pointer to memory. Let's just create a type for that. Memory is equal to this. Okay. I will get the memory, and then I need to do memory at registers R0 until until I know what. Oh, I need to stop it while let n is equal to memory. I'm guessing register R0 as u size. Like so, iter position x is equal to 0. Like so. This is the end. Let's start equal to this. Start, and this is start end. Okay, yeah, sure, I can borrow that. I can do this as well, and yeah, the position we'll unwrap it if it doesn't exist. Okay, rust string from no str from UTF-8, I guess. From UTF-8, how this takes a thing. And so that's a bit weird. Hi, this is CPN again. Now I can't chat on that account. I don't know what the hell is going on. What the fuck? How many accounts do you have? Yeah, maybe that's why you're getting banned. You have like 3 different accounts. That's suspicious. But that's weird. I don't know. I've kind of disabled moderation already. Do you mean you're getting banned from YouTube or you're getting banned from my streams? Salut, tu comptes faire une série de vidéos sur Rust après la série sur C? So yeah, the question was, do you want to do a Rust series? Je sais pas. Je sais pas, je vais essayer de faire quelques vidéos en Rust, juste pour voir, un peu tâter le terrain. Pour l'instant, c'est sûrement moins populaire que c'est. Mais oui, peut-être. Je suis en train de travailler avec Rust actuellement, donc si j'ai des petits bouts de connaissances que je peux mettre sur YouTube, je ferai ça. Et si je deviens vraiment assez bon en Rust, je ferai des vidéos un peu plus longues expliquant les concepts un peu plus compliqués. So yeah, we'll maybe do a series on Rust. Poum, poum, poum. And so in his code, yeah, there, he just treats the thing as a regular car. Well, I can do that as well. Let string as u8. String is equal to maybe just string as this, and then we do iter map wide wide as u8 like so, and then it's like str from UTF-8. Forgot how it's called. From UTF-8. STD STR? STD STR from UTF-8. And this returns a result. Can I do like unchecked? Yeah, sure. Uncheck this. Oh. The reference expression. What am I doing wrong, compiler? Tell me. Oh yeah, right. I forgot to dereference this. Oh yeah, I need to... This needs to be a slice, so I need to collect... Oh. Can I do like bytes, like so? This, and let's just collect them into a vec of u8s. And here I just do bytes, like so. Because you're changing the type notation, yes. Call to unsafe thing, oh. Sure, whatever. Unwrap. Alright, finally. Might I ask why you used Rust? Because I use it at work now, and I just want to get better at it, I guess. And also, well, for small projects like this, it's not the best language, especially for like dealing with, I don't know, low memory stuff. Well, I guess it's good in the sense that it will be safe. Or it will be safer and it will be easier to spot like the runtime thing. But like for like a personal project where you just want to learn, it's not great, I think, because it's a bit too complex. But yeah, when you're on a larger project with other people and like runtime errors are actually a huge problem, Rust is nice. I can't chat on any live stream. I'll look into it later. Huh, that's weird. I mean, Shadowban. I don't think you understand what Shadowban is, but sure. I've joined the GMTK Game Jam. I don't know what that is, but good luck. What's your opinion on Zig? I've written Zig like once in my life, and I had to create my own allocator, and then I never used it again. I mean, okay, no, it's not that bad, but yeah, I don't know. I'm too lazy to learn new languages, you know. I learn one new language every year for Advent of Code, and that's it. Last year it was Odin, the year before that it was C++, the year before that it was Rust. Zig is best. Yeah, I think like argumenting about like the new programming language is a bit cringe. Like, you know, you have the Rust, Zig, Odin, then C people. I don't know, just experiment and do whatever you want. In the end, it's the programmer that matters. I wasn't here on the first line. Can you quickly sum up the... Ah, yeah, sure. So it's kind of a toy VM. Like it's you write a VM to just learn about how to make a VM. It uses like the LC3 instruction set, I guess, which is kind of an educational instruction set. It's very small and very easy to parse. And yeah, I'm just following this tutorial along, and basically at the end of it, you want like to get a thing that can an executable that can get machine code, an executable, and just runs it. So yeah, that's it. Yeah. And then I guess the next step would be to make an actual assembler for this, which would be fun. I think it would be even easier, to be honest, but well. So now I just need to put that on std out. So currently I'm out implementing like the trap opcode, which is a special one where it allows you to do, it's kind of like doing a syscall in a regular language, regular assembly. So there is a trap called putS where you read some bytes from memory and then output them to std out. Rust put string on std out. I know there is that like the print macro, but I just wanted to check. Well, Rust std out. I'm sure I can just get this, yeah, and then this. I can just write all like so. Yeah, that works. Std io std out. Write. Sure, write all. I think I want to write all, and then it's just... Oh, I don't need to convert it to a string. Okay, never mind. Then just need the bytes, like so. Ah yeah, I need to... This is in a trait, use std io write. Yes. And write all returns the result, which we can again wrap because why not? And let's just put that up there. Okay. Can I compile? Yes. Okay. So maybe I should do another one as well. Or maybe I just keep following the tutorial. Notice that unlike C-string, characters are not stored in a single byte, but in a single memory location. Memory location LC3 are 16 bits, So each character in the string is 16 bits wide, but okay, it just converts it to a 1 byte thing. To display this with a C function, we need to convert each value to a char and output them individually. Okay, sure, that's fine. That's all for this routine. The trap routines are pretty straightforward if you are familiar with C. Go back to the specification and implement others now. As with the instructions, the full code can be found at the end of the tutorial. Trap routine cheat sheet. Okay, he just there is a get char, there is a just output one character, prompt from okay, sure. Output string. Alright, sure, that's fine. Loading programs. We have mentioned a lot about loading and executing instructions from memory, but how do instructions get into memory in the first place? When an assembly programming is converted to machine code, the result is a file containing an array of instruction and data. This can be loaded by just copying the contents right into an address in memory. The first 16 bits of the program file specifies the address in memory where the program should start. This address is called the origin. It must be read first, after which the rest of the data can be read from the file into memory. Okay. That's kind of like bootloaders, where you need to put your code at a specific address. I mean, I guess it's the same for all programs, but like part of the job is like done for you by the assembler or the compiler, where it converts your main function and it puts it at that address, or your entry point at that address specifically. Okay. But that I already done. I already did in the main, where I just read stdin and converts it to U16s, and then I put it in memory. So yeah, that was it. Notice the swap16 is called on each loaded value. LC3 programs are big endian, but most modern computers are little endian. Oh. Okay. So, well, it seemed my thing seemed to work when I tried it on a test machine code. So I'm gonna keep it. But let's maybe leave a note. Machine code is big endian. Okay, endianness refer, yeah, I know what endianness is. Let's add a convenient function for read image file, sure. Memory mapped register. Let's see. Platform specifics. Linux. Huh. Okay, sure, yeah, that's to change the terminal thing. All platforms. Download the assembled version. Oh, that would be nice. Okay, you can run like games on it. That's kind of nice. I wonder how they wrote this. Did they wrote everything, a whole game like this in the very small assembly language? That must be a nightmare. Debugging, alternate C++ technique, sure, doesn't matter. Contribution. Yeah, nice. LC tree in LC tree. Oh, that's fucked. Wait. Wait, it said LC tree in LC tree, but it's just command Lisp. What a scam. What a scam. Alright, I think I will stop the stream because I need to eat. And also, I think I will just implement a lot of the easy stuff by myself and clean up a bit. And then, yeah, I'll come back if there is any more interesting stuff to do. Because now it's just implementing instructions and implementing traps, and that's kind of like, I think if you've done one of them, you've kind of done most of them, maybe except the jump thing. And yeah. And basically after that, that's it. I can just download some object file and see if they work. Huh, maybe make an assembler after. Anyhow, I will go eat, and yeah, see you. You should try it out if you're interested in learning. So yeah.